5, 4. This meeting's being live streamed.
Okay.
So I believe we are ready to go. We have 2 participants, one live on Zoom and another live on Persona. And today, Vasu and I will be treating one of the most essential and elementary constructions in differential geometry, and indeed in geometry and topology in general, which is the de Rham theory of differential forms. Now, those words may sound scary and invoke various nightmares about cohomology and homotopy groups, but when it comes down to it, the concepts are essentially simple and essentially unique, and they all reduce to, at the end of the day, the most intuitive topological idea, which is called the number of connected components. And so before we even begin the lecture, let's talk about what that means. Intuitively, we all know that if someone hands you a space, you can look at that space and judge for yourself how many connected pieces does the space fit into. So, the planet Earth approximately seems to be one connected piece. Yeah, unless like an asteroid strikes it and a big chunk of the planet Earth floats off and we have 2 connected pieces. Most simple shapes that one encounters in life, we usually consider them as one connected component. And I'm not going to necessarily dwell right now on the definition of connectivity, but just rely on your intuitive notion of what it means to be connected. It just looks like it belongs to one piece. The essential idea is that everything in topology in the realm of homology or cohomology or homotopy theory reduces to this idea of the number of connected components. And in particular, the theory of differential forms can be understood as measuring the number of connected components in various dimensions. And the de Rham theory expresses this essential topological information in terms of integrals, like analytic integrals of say, smooth or analytic functions defined on the space. And today, we'll see exactly how that happens or how that comes to be. So,
yeah, I mean, just as a bit of commentary, I have a vague sense for why it is you say the differential forms in de Rham homology is telling us essentially about the number of connected components of some space. But it's not manifest in how it looks.
It's not obvious. No, it's extremely non-obvious. I mean, in some sense, there's this is how the theory was invented, but it is not how it is presented, which is just typical in physics and mathematics as it's practiced today. It's almost like a sleight of hand, right? Like the actual idea that led to the discovery is either forgotten or it's swept under the rug. Who knows why? But the goal of this podcast series is to reverse that, and we'll do that for the theory of integration today.
Another fun fact is the connection that Britain found between de Rham homology and supersymmetric quantum mechanics.
Right.
Supersymmetric quantum mechanics. The basic idea is that you throw a free particle on a manifold. Right? Free particle with energy measured by the Laplace operator on the manifold. And you will in fact see that if you extend this in space by some Grassmann directions, then the particles, the partition function and the related quantities like the Wick index, compute things like the Euler characteristic.
Right, of the manifold itself.
And from that perspective, it would be very fun to give us a cartoon view of what it is you're talking about.
Absolutely. And I mean, we can be very precise there because the different degrees of the cohomology complex there are measuring in a precise sense that will, in 5 minutes, you'll see very precisely in what sense these are measuring the number of connected components or equivalently the dimensionality of holes, like in that degree. So we'll see precisely that these correspond to states in that quantum mechanics.
Correct.
Excited states, essentially.
I even have notes on that, so
Yeah, we can dive into that immediately after. So yeah, let's do that. We'll start with a more abstract presentation of essentially loop space geometry, and we'll end up at some supersymmetric quantum mechanics. I think that'll be quite wonderful. So we'll be following some notes, like pretty legendary notes of Raoul Bott from some lectures that he gave, I think in the 80s, on the origin of integration and de Rham cohomology theory from these intuitive topological ideas. So I highly recommend, if you've never looked at them, you really ought to. So let's begin. So the basic idea as we started is, given a topological space, you can ask a child, how many connected pieces does it fall into? And this speaks to something quite primal. I mean, we have something in our brains that, either come fully equipped in order to do this kind of classification problem, or we learn it at a very, very young age. And the observation is that this is the fundamental idea you need to really understand cohomology and homotopy in all of its nonlinearity. So let's see how to do that. So we won't define cohomology first. In fact, we'll define something that on the nose seems much, much more complicated. Mm-hmm. And this new thing we'll define are called the homotopy groups, or the homotopy invariants of any topological space. So schematically, you should think that given a topological space, there's a number you can extract from that topological space, which is the number of connected components it falls into.
Right.
But what we realized is that this number essentially admits a unique generalization to a sequence of numbers indexed by 0, 1, 2, 3. When we ask what's the number for 0, which we denote as pi 0, or the 0th homotopy group, what we're really asking is, what is the number of connected components or zero-dimensional holes in your space? And we're going to generalize that higher dimension. So we're going to figure out, what is this higher connected component concept in degree 1, 2, and 3? And we'll see that it is essentially unique. There's only one way to do that. So let's.
So can we pause for a moment?
Yeah. I can also.
On a technical note, what's happening on YouTube, it looks like, is that since the audio is been fed into my mic, it looks like there's someone speaking back.
Oh, I see. So do you want to pull up this PDF?
Or you can just
What
scoot over so that you're in my camera.
Ah, perfect. Yes, that works. That works super well.
Yeah.
Do you want to bring it? You can come over and then we can sit next to each other.
Yeah, let's do that. Sorry for the interruption.
So we've got enough space. Okay, so we'll start off by observing that the very first quantity we will assign to our given topological space. Remember, the game we're playing here is someone hands you a topological space. You can think of something concrete like a ball or this genus 3 topological surface that's depicted here. And the game is, how do we take this complex nonlinear quantity, this topological space, and produce something that is much more manageable, that describes something essential about the space? So you can think, like, in the context of all possible spaces, we're putting coordinates, right? And it's highly nonlinear coordinates. They don't behave like the usual coordinates do, but the simplest possible coordinate you could assign to such a nonlinear quantity is the number of connected components it falls into. And we'll denote that as pi 0 of x, where x is the topological space. So if you want, there's a natural immediate generalization to this, which is, we can make pi 0 of x a pointed space, which you can just think of as coloring the connected components. So, every point is going to belong to a unique connected component. And so if you distinguish a point, so you're not only thinking about spaces, but you're thinking about spaces with a distinguished point, then with a distinguished point, so a choice of a single distinguished point, we'll denote that pi 0 xp, then you should think of that as the same collection of connected components, but there's now a single one that's singled out. So this is just an accounting mechanism. Nothing has really changed. We're just remembering that the point belongs to a certain connected component. And the reason we're going to do this is because in order for me to construct pi1, so the higher dimensional generalization of pi0, this higher notion of connected components, it's really going to, the construction is going to depend on the choice of the point. But what we'll find is that that choice of point, actually, the answer is the same for every choice of point. And this is the first theorem in the Durand theorem. This is like the first fundamental theorem, is that, you know, you make the construction relative to a base point, which we'll see in a second, but the choice of that base point makes no difference.
I see.
And in fact, you can tell how changing the base point changes the construction is part of the theory. It's completely accounted for. So now in your mind, you should think, you have a topological space like this one over here, and you've singled out a single point, which we call P. And we're going to construct a new topological space. And we're going to measure the number of connected components of that new topological space. And this is what pi1 is going to be. So what is this canonical construction? Well, we're going to denote it omega sub p of x, which you should read as some construction omega, which depends on p applied to x. And this is really just the space of continuous maps from a circle, which you can think of as embedded inside the complex plane, which sends one distinguished point, 1, say, it could be any point, but let's say it's 1, it gets sent to P. So we're thinking of sending continuously a circle into the space. So we're probing, this is the loop space. We're probing all what's the base loop space, loops that are based at P, and this is where the dependence on P comes in.
Okay.
And so we started with our nice genus 3, you know, 3-hole donut, and now we construct some huge infinite dimensional space, the loop space that's based at the fixed point. And so you can think of varying the point P, and you're constructing a family of infinite dimensional spaces as P varies. So now you can ask, what are the path-connected components of this based loop space? And this is the formula that I just said in words, which is that pi1, so the first higher dimensional invariant, homotopy invariant of x, can be defined as the regular intuitive invariant of this new based loop space. And where is it based at? It's based at the constant loop. Right? So you need to, we're dealing with based spaces here, which means that every space comes distinguished with a point, because we're like remembering which connected component belongs to that point. It's not essential. It's essential. Like you could forget it at the stage, and then the language becomes a bit more complicated. But essentially, what we're saying is a point P. A point does not matter. But at the end of the day, it's the answer. At the end of the day, it's prove it. But now you fix this point, and you construct a loop space. So this is the space of all possible circles. And this allows degenerate circles. So you can imagine the whole circle sent to P. That's one loop. You can imagine a circle that like wraps around the topological surface. You can imagine a circle that wraps around one of these loops. And they all start at P and they end at P. So that's the constraint of this base loop space. They all start at P and end at P. And when you calculate the number of connected components of this new space, now you have a new number, which you might ask, it might be infinite, because, okay, this is an infinite dimensional loop space. Like, how do I know that there are finitely many components? It turns out if the space is finitely generated, there are only finitely many components of this loop space. So what does that mean?
So,
sorry.
Just to backtrack.
Yeah.
So you lay out the very basic notion of what pi0 is.
Yes.
Pi0 of x is like
pi0 of anything is just
the
number of pieces. Yeah.
Number of pieces. Right? And that's easy enough to imagine when you have
some simple
space, exactly. Right? Presumably finite dimensional. Now, when you have the space of maps from the circle into the space you had before.
Yeah. How to think?
That's now this infinite dimensional thing.
Yeah.
And what you're saying is that the higher I1, sort of higher dimensional generalization of this the number of connected components
Yes.
is the number of connected components of that infinite dimensional space of maps.
Yeah, that's right.
So just to get some intuition, something to hold on to.
Absolutely, yeah.
You have so having disconnected components, right, of any space means that there's like pieces that you just can't move from.
Absolutely, that's the fundamental idea. That's absolutely correct. That is the key idea. It's like, if you want one formalization of this is, if you had two pieces and they're disconnected, then there's no continuous path from the one piece into the other. Now, what you really, I see what you're reaching for, Vasu, and I want you to try to complete the idea. What does that mean in the loop space? What does it mean that there's no continuous path from one loop in one component to another loop in another component?
Right. So presumably this distinguishes loops that, like wrap those holes or something.
Absolutely correct. Because a loop that wraps this hole without cutting and tearing it cannot be deformed into a loop that wraps this hole. Similarly, a loop that like wraps around this handle cannot be continuously deformed into a loop that's like starts here and then like goes around and ends here. But that one could be shrunk to a point, to the trivial loop, whereas like the one that's like over here would have to pass over the hole. And this is exactly the sense in which connected components detect holes.
Right.
So when your connected component is in the space of like probes of your space, which is fundamentally like a probe is like asking, is it a hole? Because it's a circle, right? The circle has a hole. Fundamentally, it has, we know, one hole in dimension one, essentially, right? But if you embedded the circle, say, into a planar region, right, in which there's no hole, then you can continuously shrink that circle down to a point. And that's telling you that the connected component of any circle in the plane is the same connected component as the constant map. And so the plane has no holes. And now we've just computed pi1 of the plane, right? It's trivial. There's one connected component.
Well, that's okay. That now makes sense.
Yeah. So you see the game that is emerging. It's like we've translated this kind of difficult question of how many n-dimensional holes are in your space to a much simpler question of how many connected pieces are there in a much more complicated space. So like we push the complexity around a little bit, but it turns out that even though this is the next point, it is extremely difficult to compute these groups. Like presumably extremely difficult, but nevertheless people have done it. Like it's better than nothing, so to speak. So somebody has done it. Some very smart people have thought their whole lives, and then they compute like pi3 of the seven sphere. And then it's like a huge paper. It's like it's like our knowledge advances like by by decades, basically. So, I mean, a couple remarks should be in order, which is that actually these objects, like these sets of connected components, have a group structure, which is not at all obvious.
No.
So these pi0 is not a group, but pi1 and higher is a group. So what is that saying? It's saying that up to continuous deformation, you can actually put a group structure on loops up to moving them around. And what does that mean? It's concatenation. So it means like you follow the loop, and then you follow the second loop. Yeah, that's the product. That's the product. And
then the inverse is you just.
This is not a correct. You go in the other direction. That's correct. So this is not a strict product in the sense that it's only a group structure if you allow continuous deformation and reparameterization.
Oh, okay.
Because what does that mean? It means like a map from the circle is going to be different depending on the speed it goes around the circle. So if you concatenate two maps and their velocities are like slightly off, it should be the same path as like a different reparameterization. So, it's easy to see the group structure once you admit reparameterization. So the way mathematicians will say is that it forms a group up to homotopy. And if you think a little bit already, pi1 is not abelian, it's not commutative. So I'm not going to prove that right away. Or we can give an example, like pi1 of this space is already non-commutative. It's
Right.
essentially generated by 6 elements
Yes.
subject to the commutator relation.
Which are basically the two kinds of ways in which you can go around the whole.
Absolutely correct. Absolutely correct. That's right. And this, you know, this bracket is just standing in for this commutator expression, which is exactly, you should think of it in the group structure. It's like you're concatenating the pods, and then you can just take it up to reparameterization, and it's clear what the group structure is doing. And then it's just saying, like, if you follow, you know, there are, the way you should read these symbols is that there are generating loops. There are generating holes that are like distinguished from the identity, right? They're different from the trivial loop. And so each of these represents some topological obstruction to triviality in the space, which you can think of as one loop around this way and then another loop around this way. And then that's why there are exactly 6. And a little bit of thought and exercise for the viewer is trace it out, draw it out on a genus 3 Riemann surface, what it means to like go around one of these loops and then another one like this, and then to do the inverse in this order, and convince yourself that you can contract the result down to a point. And
why that's the
you should also think about why the commutator is showing up here. That's actually a deep fact. It's an extremely deep fact. I mean, sort of this type of commutator relation in essence defines the Riemann surface's topology, which is this next statement that, in fact, pi1 is a one-dimensional quantity, which we can intuitively reason about when we're mapping one-dimensional probes into maybe a 2-dimensional space. And when we measure the number of connected components of like the totality of these one cycles, we're getting a one-dimensional invariant. And it turns out that pi1 is completely sufficient to classify all topological surfaces. So if you know this invariant, pi1, along with its group structure, you know the topological type of the Riemann surface completely. So knowing the number of holes is completely deterministic for the topology of the Riemann surface. You know, there's some degree of freedom for the Riemann surface itself, which is the complex structure. There are these 3G minus 3 moduli on top of it. But for the underlying topology, that's fixed. Once you know this group, you know the topological type, you know the surface.
And how much of this carries over to surfaces of dimension higher than 2?
Everything does. Almost everything does, is the point. So in the general case, now we can define pi k.
Yes.
And how do you do that? Well, you just iterate the construction. And this is what is so essentially beautiful about this theory. Well, you know, if pi1 was pi0 of the loop space,
yes,
pi2 is going to be pi1.
The number of holes in the
exactly. So you can think of that as like, if you unwind it, then that means you take another loop space and then you measure the connecting components of this double loop space. And when you really unwind it, what you find is it's not the number of connected components in the space of spheres.
Right.
Or pi3 is the number of connected components in the space of 3 spheres.
Right. So basically, it's like instead of trying to wrap with the circle, you're wrapping with the sphere.
Yeah.
Or whatever.
Which you should just think of them as models for holes. Yeah.
Correct.
Spheres are like the simplest topological space that has a hole. I mean, we're going to see this.
Basically, the fact that this is what you're getting from pi2 is just because you have like 2 circles.
That's correct. Yes.
I see.
That is correct. That is correct. So, I mean, the calculation there, and it is a calculation, you should do it at least once in your life, which is you should ask yourself to be very clear about what it means to draw a loop inside the space of loops. And let me do it in the air for you right now. Just imagine a sphere, right? And imagine parameterizing this sphere as like, you've got a point, the north point and the south point, and you've got like a family of circles. So you can imagine this is actually a loop in the space of loops.
Yes.
Starting at the trivial loop, which is a point, and it goes off and it like, you know, spans out up to the equator, and then you start undoing it by coming back, and this is essentially the idea of the proof.
I see.
And this works in arbitrary dimension. Exactly the same idea works. You can use induction to arrive at higher dimensional spheres this way.
Why is it not a torus?
Well, if you took the literal product, it would be a torus, like S1 times S1. But, but we're not taking the literal product. We're not taking maps from S1 times S1 What we are taking is maps from S1, the circle, into the space of loops.
Into the space of,
Yeah,
right.
so we're iterating. So you start with X, and then you form the loop space, all loops in X.
Yes.
And then we're forming the loop space in the loop space.
Yes.
And so it's not that we're asking for maps from S1, the circle times the circle into your space.
Correct.
It's that you're asking for maps from the circle into the loop space.
Right.
And that's why if you move inside a loop in the loop space, based at the constant loop, the trivial one, then you're necessarily going to expand, like any perturbation of the trivial loop is going to expand the trivial loop into a non-trivial loop. Yeah. And if it comes back to the trivial loop, then it has to at some point contract.
Oh.
And that's exactly the sphere. So now you see like the.
Yes, I see. No, that's something.
Yeah. So what we're saying now is it's just pure induction. Like if you want to define pi k plus 1, you literally just need to know pi k, and you need to know the loop space of X. And unwinding that means that as you evaluate pi k, you're taking higher loop spaces. You just keep like loops into loops k many times, and that's exactly where the sphere comes from. Yeah. So this allows you to simplify the formula down to just pi 0 of some space. So you just, something very complicated is going on. We might be like detecting holes, but at the end of the day, we're just asking how many pieces are there in some abstract space. And the answer always boils down to some number. And there are a couple magical things here that are just being swept under the rug, which is how do these infinite dimensional spaces have finitely many components? How do you get a number? It's like, well, why aren't we getting like an infinite?
Right.
So, I mean, it turns out you don't have to. You can get infinity, but if it's finitely generated, so if your topological space is built up out of cells, which, just very roughly, intuitively, you can think of simplices in n dimensions, so like triangles. So a zero-dimensional triangle is a point, one-dimensional triangle is like a line bounded by two edges.
Right.
Two-dimensional triangle is like a literal triangle, three-dimensional triangle is like a tetrahedron. And you can imagine just gluing these things together in some nice way to get a topological space. Let's say this is finite generation. When you do this, the numbers you get are all finite.
Right.
And you can maybe believe intuitively why that might be true.
Sure.
Because each of those pieces is finite. And when you glue them together, you just allow new deformations. So you end up with something that's inherently finite. But there's another deep fact that we're hiding here and was mentioned earlier, which is that if you have 2 points in your space, right, and they're in the same connected component, then actually you have an isomorphism between the groups. They're the same groups. And the way to do it, in fact, is to draw a path between those 2 points and imagine this induces a conjugation action on loops. So just imagine you can transport a loop based at one point to a loop based at another point using the path. So how do you do that? Well, you start at the point, you move along the path, you follow the loop, you go back. Now you've just mapped any loop from the one point based at the one point up to deformations to a loop based at the other point up to deformation. And every path between these 2 points will give you such an isomorphism. So now you get an additional, like, pretty strong bit of data. You're lifting nonlinear topological quantities, which are paths between 2 points, to algebraic isomorphisms between groups. And it turns out, and this is another part of the depth of the theory, is that the homotopy equivalence class of the path, that is to say, as you're like moving, you can imagine maybe the path's a straight line, or you can like wiggle it around a little bit. And as long as you're doing continuous deformations like that, you get the same algebraic isomorphism.
I see.
Whereas if you started with a different path that cannot be continuously deformed into the first path, so you've got 2 points, P and P prime, and you've got 2 paths between them. Imagine there's some hole or a tear somewhere in the space. You can't continuously deform the 2 paths. Then that actually selects 2 non-equivalent isomorphisms between the groups. So the groups, the moral here is that the algebra is like a canvas that's receiving the topology of the information. It's like the groups are rich enough to like detect all the non-trivial topology that's actually going on, which I mean, I think it's not a stretch to say that the idea that we just gave, this is the entire point of category theory and functional reality, in fact, is the birth of homotopy theory and modern topology, is the observation, which goes back a while, that these highly complicated nonlinear topological deformations that you can do can in fact be completely captured by these very rigid algebraic objects known as groups. So
That is very fascinating.
yeah,
And deep.
no, it's extremely deep. I mean, I cannot emphasize enough the depth of the ideas just exposited, and they seem so simple, but they are the basis for all of homotopy theory. So like whatever homotopy theorist does, they're really building fundamentally off like some of the ideas that we just discussed today. So maybe we can just very briefly talk about for the Riemann surfaces that we kind of hinted at, like we've spoken about the sphere, that's a genus 0 Riemann surfaces, the torus we spoke about, it's a genus 1 Riemann surface, and up here we had a genus 3 Riemann surface. For these, all the higher pi k's beyond 1 are 0. And I mean, and in fact, sorry, above 2 are all 0. And that is essentially why we only need pi 1.
Yeah, but presumably that's because it's a three sphere. That's just too high dimensional.
Absolutely. No, that's the fundamental idea. I mean, there's just like, there's more going on in the three sphere than any Riemann surface because of the extra space. That's correct. And that is detected by the fact that this three sphere is going to have a non-trivial homotopy group, dimension 3, which detects the hole, but no Riemann surface is going to have that hole. Like just intuitively, it's not possible, right? There's not enough space. So, I mean, basically, now you can arrive at Hurwitz's idea, which was really profound and is quite recent. I mean, it's 100 years ago, essentially, that this idea came to humanity, which is that this sequence of numbers, and the richer version, which is not just the numbers, which is the number of generators of the group, which might be infinite, but the group itself is sufficient, in fact, to understand any topological space up to deformation. So you can say that, like, in the game you're playing, well, you know, a topological space is a set with some structure, and you know which points are near which other points. But if you're a little bit more clever and you say that a topological space is up to homotopy, an equivalence class of these spaces, up to continuous deformations, so you know, like the surface of like a coffee mug is still a sphere, you know, if you want to think of it in that way, then it turns out that knowing the groups completely determines the class. Like that's it. There's no more information. Once you omit these deformations, then the groups capture everything. They detect the class precisely. So that means you just need a sequence of groups, and they're just measuring the connected components of these higher loop spaces, these iterated loop spaces, iterated based loop spaces, to be even more precise. So to reiterate, okay, it's very beautiful. We've just defined something so general that applies to every topological space, but the caveat is that it's extremely difficult to compute. So how difficult? Take the two-sphere, take the the Riemann sphere of genus 0, right? It turns out we don't know all the homotopy groups. Like, go high enough and we just don't know what pi k is. We have no idea how many connected components. I mean, it's enough to know pi 1. Like if you know pi 1 and you know it's a two-dimensional surface, then you know which Riemann surface it is. So in that sense, the coordinate system like completely selects out in the space of topological surfaces, which are the two spheres and which are not. Like in particular, the two sphere has pi 1 is trivial. And that's intuitive. Put any circle on the sphere, and then you can just continuously shrink it to a point. So there are no one-dimensional holes in the two sphere. But it turns out we know pi 2 intuitively. Well, there's one sphere, there's a generating two sphere in the two sphere. But then if you try to go higher, it's not clear. Like it's not at all clear. We know that, like, you know, some of them vanish, but we don't know. We don't have a proof. So it's like expected that they'll vanish, but we don't have a proof. So there might be something weird going on, but it's just unknown. So we have discovered many computational techniques that have allowed like extraordinary progress. And it should be said, for spaces such as the spheres, which themselves are the basic probes for homotopy theory, the fact that we don't know all the homotopy groups of the spheres, that is to say, like how the spheres relate to each other, is just a fundamental problem for topology and mathematics in general. And when we discover new computational advances, then we discover new progress throughout math. Because, you know, if you discover something new about the seven sphere, like it's a basic probe for every topological space in existence, it allows us to define the Durand theory, even in this particular approach, and understand what it means. So you can think that, like, even though progress is hard, what progress that does come is like absolutely essential. So there is, how to say, one really essential way of expanding upon these ideas, which is what leads to the Durand theory, and that's what we'll investigate today. This is what touches on in coordinates explicit integrals, which we're about to see. It in fact describes why the topology of a space governs what kinds of integrals are possible on that space. And this is usually called, the idea is usually referred to as cohomological extension of the component concept. So the component concept is just this intuitive idea of how many connected components are there. And we're going to generalize that number again. So we generalize it in one way to like sort of up in dimension. And now we're going to generalize it for each of those numbers. We're going to derive a new number called the cohomological shadow or the cohomological extension, which in fact is a simpler number. In some instances, it agrees with the original number, but in many instances, it doesn't. And it is also much easier to compute. So we can actually compute this new number that we're about to define. So it essentially follows. So there are two ways of saying it, which is that, first of all, the cohomological, the approach we just took has can be described in a point of view or a reference frame as homological. So what that means is we're actually studying cycles in this space, right? We're mapping spheres, which you can think of as submanifolds, and we're taking those submanifolds up to equivalence, and those are what mathematicians call cycles or homology cycles. And you know, depending on exactly what the deformation that you consider, it could be up to homotopy, and then you get these homotopy groups, or it could be up to something a little bit stronger or weaker, and then you can get a notion of homology. But the cohomological extension of these new numbers that we're going to define is actually a dual point of view. And this is in the vector space dual sense. So that means instead of dealing with a space, we're going to deal with functions on this space. So let me take a moment to talk about what duality means here. Like, take a vector space, right? What is the dual vector space? Space of linear functions.
Because the point is, the point of the dual is to be able to take a product with the original thing and you get a number.
Correct, absolutely. So how that means you need to be able to take a function and you need to be able to take a point and then you can evaluate the function. And that pairing is exactly the kernel of the duality. So we're doing exactly that.
You see, that's the, okay, so just to sort of ignorant physicist sidebar comment, that basic instantiation to pairing isn't something that a lot of people might appreciate.
I think that's correct. That's absolutely correct.
In some sense, there's actually a pairing between point and a function, point and a map, rather than, you know, starting with like a vector.
Exactly. Which is usually how people tend to talk about it, but it loses the essential simplicity of the point of view. And actually that applies here directly, because the perspective we just took is we're mapping things into our nonlinear space. We're mapping circles or spheres of higher dimension into. And the dual point of view is you map out. So you take X and you map from, take X and you map it into like the real, the complex numbers is one way to do it. And from that point of view, it motivates why functions enter the game. Because functions are the basic constituents of maps from. Like they're the simplest. You could map into a circle, and people do study that. And that's more in the homotopy sense. And what we're doing is this cohomological extension or shadow, which is much simpler. So instead of mapping into a circle, we'll map into just the real numbers or the complex numbers. So that means, to really spell it out, we're studying functions. and now you might see where the integrals are going to come in. So the first starting point of this simplified theory, which is dual to the original theory, it's taking place in the dual frame, is that every locally constant function, okay, so if you have fix a component, right, you can detect this component by saying that every locally constant function is actually globally constant on that component. Like if you're only dealing with a component,
Yes.
right, there's this extension principle that's more or less intuitively clear. It's saying, well, if it's locally constant and I can like move along and I can just keep doing that, then eventually I'll hit the bounds. Nothing bad happens.
And the bad thing that happens is
that you leave the component. So if you rule out the bad thing that can happen, then now you have a dual characterization of what a component is.
Yes.
A component is something such that every locally constant function expands to a globally constant function.
I see. So in other words, you can use the constancy of the function as a probe for
absolutely
like its argument, right? Like it's sort of telling you how far the connected component
absolutely goes. Correct. And that's, so remember, we're playing the same game. We're just playing the same game in a dual reference frame.
Yes.
So before we could literally intuitively just ask how many connected components, we could eyeball it, right?
Yeah, well, that's the thing. In some sense, the function is the eyeball.
Yes, that's correct. No, that's absolutely correct.
So, I mean, well, if you take another perspective, it's like saying that you have a classification task, and the output, I mean, what is a classifier? It's a function that says 1 or 0, for instance.
Yeah, absolutely. No, and you're hitting the fundamental idea. So now we can define a new group, which is dual. It's a simplified dual version of pi 0. So pi 0 was, you know, actually in some sense, pi 0 can be defined as like equivalence classes of maps of points. The 0 sphere, like, you know, the simplest sphere. It's like, so you map a point in and then you allow it to deform, and this is what detects the component, right?
Yes.
But now we're going to map out or from X into the real numbers. So the simplification is we're not mapping into a point, but we're mapping into an actual number system, which makes it simpler. Why? Because we can add and multiply functions, right? So we get some extra algebraic structure. We get a vector space structure. So now we can define this H0, which is really the 0th de Rham cohomology group, but we won't call it that yet. And it's literally the vector space, and it's a vector space you can add two functions pointwise, and you can scale them by real numbers. And it's just real valued locally constant functions, just the probes, right? And however many there are, that's how many connected components there are.
Right.
And exactly as you were saying, because these functions, you can write a basis, like given by 1 on one component and 0 everywhere else.
Right,
exactly. And scaling that, you know, detects the different components.
Right. So it's in some sense like a basis of classifiers for each component. Like it detects.
Absolutely. So there's a little bit of subtlety that I swept under the rug here that I think we shouldn't go too into, because for every space a physicist is ever really going to deal with, the two notions of connectivity that you have agree that we've used here, and that's path connectivity and just general connectivity, topological connectivity. So most of the time these two agree. That is to say, if you can draw a path between 2 points, then they are the same as topological connected connectivity. But there are some like pathological spaces in which they don't actually agree.
That's cool.
And it is cool, but it's not really relevant for what we're dealing with. I mean, they're very weird spaces. They don't satisfy any like standard geometric intuition. So that's one way to think about it. So for most reasonable spaces, we now have two expressions of the same number, either as like literally the number of connected components, or as the dimension of this new vector space that we just, and again, here the two concepts are dual to each other. Right. The first is mapping some contractible space.
Yes.
So like the unit interval is the same up to homotopy as the point, as I mentioned earlier. So you can think of it as a homotopic point or an interval, whatever. The interval makes it clear that we're detecting path connected components because, you know, like can bound it. Yeah. But that's the same as using maps of X out or from X into the real numbers to achieve the same purpose. So we have two dual reference frames, and you know, if we simplified on both sides and we simplified using like simplices or something, then we would end up with homology and cohomology, and they would literally be dual vector spaces. But we just introduced the non-simplified version. So there's actually like 4 constructions. There's homotopy and cohomotopy, and we've like looked at the diagonal. We've looked at the homotopy groups, and we've looked at the cohomology groups.
Yes.
Which, if you could define the cohomotopy groups, which one can, then they are the more advanced, more complicated version of cohomology. And in fact, there's a map going down. You can simplify the homotopy groups to the homology groups, and it's quite wonderful. It's just, it's an abelianization type of map. So for example, for pi1, if you kill all the commutators, you literally get the homology group. It's a little more complicated with the higher groups, but there is a way to relate these 4 possible constructions. And really, really important for calculus is that the cohomology group H0, unlike the group pi0, has a flat vector space structure, right? Like it's actually a linear space. That's because we had pointwise addition and multiplication of these locally constant functions. So now we can play the same game, and this is exactly where de Rham theory naturally falls out, and it's where the theory of integration and differential forms takes on its fullest meaning. Is just like we took pi0 and we generalized it to pi1 and pi2, one can take h0, h upper 0, 0 with cohomology, and generalize it to h1, h2, h3, the higher cohomology groups. So how do we do that? Now, one of the most fascinating observations is that there's no unique, unlike homotopy and cohomotopy, there is like a fauna and flora of cohomology theories. There are just like billions of them, and they all relate to each other, and they're all complicated and in their structure, and they all like receive maps from the homology, so homotopy and cohomotopy. So you should think like underneath the surface, you know, homotopy and cohomotopy are at the top. Underneath the surface, there's just like a very rich universe of different homology and cohomology theories. However, they all agree on reasonable spaces. So in particular, in manifold theory, like smooth manifolds, exactly, you just can't, there's no difference. And for any space in which you're actually going to do some integrals, there's most of them not going to be any real difference. So here, saying just in the realm of the differential manifolds, all of these theories are the same, and they're in fact represented by the de Rham theory. So there's a constructive approach which stems from coordinates, and in fact directly generalizes the locally constant construction that we just gave, because we started with functions. So you need to do something, you need to somehow generalize a function that is locally constant, something that is in a sense higher dimensional, and we're going to see exactly how to do that from first principles next. And this is in fact how one can invent differential forms. It's a very, it's like the most conceptual, like way to discover a differential form. It's ultimately going to be that the differential forms are a way to construct the higher HKs. And in fact, as we will see, integration theory only sees the de Rham class of the differential form. So that is to say that there's something essentially homotopic about integrals, which we know already, like we know from calculation. So maybe there's something quite magical about the de Rham theory that I think a lot of people don't fully appreciate, which is that the de Rham theory is like really, in some sense, perfect in the sense that all of these cohomology theories collapse in the real manifold locus, or the differential manifold locus, or the analytic manifold locus. But also it speaks to like physics and mathematics and all these cross disciplines in essentially like a unique way. Like, you know, differential forms have actual physical meaning. And that is highly non-trivial. That tells you that homotopical concepts have physical meaning, like essential physical meaning, right?
One thing we could even do is go through what that is for, say, we have differential forms that appear in different contexts, but let's take electromagnetism, for instance, or just in the gauge theory. And you have the differential one form, which is the field, right? Vector potential.
Absolutely.
what is the homotopy theory that it is capturing? You could ask that question.
Absolutely, and we even have the answer now.
No, yeah, I mean, we know.
We've already sketched in a sense.
But physically, what that means is you're looking at what kinds of charges.
Absolutely.
Like physically, what are charges, in this space?
Yeah.
Right? As in, if you have a one-form field, right, a one-form gauge field,
Yeah.
you're going to have point-like charges.
Yeah.
And in space-time, they're going to trace world lengths.
Yeah. Yeah.
And then if you have higher form charges, or if you have higher form gauge fields, then you're going to have extended object charges.
Absolutely correct. So we're really just reasoning in this dual reference frame,
Exactly.
where these differential forms you should think of as the dual manifestation of cycles.
Yes.
So these charges are inherently topological, which I mean, I don't think this is something they teach physicists, at least not in the beginning, right?
No,
that fundamentally electromagnetic charges are actually coming from cycles.
That's
inside
the real implication of Gauss's law. At least if we're not looking at, if we're just looking at compact spaces, right?
Yes.
The real.
Which for our intents and purposes, we're going to need that because
Yes.
that's going to give us finite numbers everywhere.
Right.
And allow us to define integrals. So for the rest of this, we can even just assume, we will very soon assume that everything's compact.
Yes. And there, that's like what Gauss's law is telling you.
Correct.
If you really work through the implications of it.
No, that's absolutely correct. So, in some sense, the benefit of this homotopical point of view with loop spaces is that we're really just saying, well, really, there are many probes.
Mm-hmm.
You could map any space into your fixed space and use that as a measurement device.
Mm-hmm.
But the spheres are just like the convenient way in which we have like induction at our disposal. And it also allows us to relate this nonlinear construction to a more linear construction involving functions.
Mm-hmm.
And I would say that these dual points of view are exactly complementary in the sense that the one is very easy to conceptually reason about and the other is very easy to compute with.
Mm-hmm.
So you need both really at the end of the day. The function theoretic approach is how you compute,
Mm-hmm.
because you can always just drop into coordinates and do something, whereas the sort of cycle theoretic point of view is conceptual. You can reason about what it means, but you can't necessarily compute anything a lot of the time. So let's actually do things extremely explicitly now. So like we're going to try to define these higher cohomology groups, the analogs of H0, which are dual and simplified duals to pi 0.
Mm-hmm.
So we're asking for the simplified duals to pi k,
Mm-hmm.
and we're going to define them purely in terms of smooth functions, like differentiable functions. So let's in fact simplify the space that we're probing. And we're just going to take flat Euclidean space, so Rn, and we're going to take some open domain. Okay, so you can imagine anything. You can take all of Rn, you can take like some bubble inside Rn of some dimension, whatever you're most comfortable imagining. And this has the benefit of allowing us to drop into explicit linear coordinates, which you should think of as functions. This x1 through xn are functions that take real values, and they allow us to like parameterize every point of this domain. Then we can take the smooth functions, so we can consider the totality of all smooth functions on this domain. And we can ask, how do you characterize the ones that are locally constant? Right, so we already determined, okay, H0 is spanned by the locally constant ones. So in order to relate a general function, we need a way to like pass from all functions to the ones that determine H0. And if we can generalize that procedure, then maybe we can end up with HK. So it turns out that there's a differential criterion, obviously, for being locally constant, which is that the gradient must vanish. Yeah, it cannot vary. And that means that if you ask what the gradient is in the direction of these coordinate directions, it has to be 0. You can allow no variation. But that is just a differential equation which can be expressed in such a form, which is to say, we can define this operator D, right, which essentially computes the gradient.
Yes.
And we can just ask if that is 0 everywhere. This is just a restatement of local constancy.
Yes.
right? So now we've just redefined H0 is the space of solutions. The equation df is 0, right? Okay, maybe H1 is also the space of solutions to some natural differential equation.
Okay.
Right? That's a good way to posit. So, well, we can use the fundamental idea of induction that appeared before, which was, okay, before the induction was taking place in the iteration of loops mapping in. But here, the induction can take place instead on the gradient differential operator applied to functions. So before we were inducting to the left, taking iterative loop space. In the dual frame, we're going to induct to the right. So we're going to take locally constant functions and we'll hit them with the exterior derivative, right? And we know that the ones, so out of all functions, the ones that which df is 0, those are the local constant ones. But there are functions for which df is non-zero, right? So now imagine taking d of that. This is the type of induction. So now we're taking the gradient of the gradient, and that's the analog of the loops into loops. So let's spell that out precisely. Let's consider a one form on the space. So we'll define one forms formally after this discussion, but here you can think of it as something that arises as the gradient of a function, right? So that is a completely valid way to think of what a one form is, right? You can express it in components as basically spanned by the gradients of the coordinates. So you have the generating one forms, which are d of your generating functions, and any one form can be expressed as a linear combination of the generating one forms. And the coefficients are themselves going to be smooth functions on the domain. So now this is where the integration really shows up. So any such one form can be integrated along a smooth path, which you should think of as geometrically, we're inside our space. This one form is really associating something like a small dual vector, right? To every point, which is to say that like to every point, like to every tangent vector at that point, it's going to assign a number. And where do you get the tangent vector from the path? Well, the path is going to trace out some literal path, and it's itself going to have tangent vectors, which describe infinitesimal motion. And our one form is literally going to evaluate each of those little vectors to a number, and then we're just going to sum all of those numbers along the path. So it's very, very elementary. We really don't need anything except our intuitions to make sense of what's going on here. So what is that saying? It's saying that, well, one cycles, paths are covectors on the space. They're the dual space in an essential way to the one forms. Because that's how do you evaluate a one form? Well, you give it something to integrate over. So the kernel for the pairing here is integration.
So but like not even integration. It's integration against space, not like
yes. It's very important. You're correct. It's very important that like the space enters in multiple ways. The space enters in the totality of one cycles that are possible. The space enters in the totality of all differential forms that can be defined on it. And then the space enters in the fact that you need to be able to make sense of the integral. So now we can ask, okay, remember the inductive procedure involved doing literally the same thing at every stage of the induction. Like we didn't change what we were doing, we just changed the domain where we were doing it. So, you know, if these cohomology theories are supposed to be an essentially dual, simplified, but essentially dual manifestation of what we just saw, then we really should be doing the same thing. So we try to do that. Well, let's ask which differential one forms, out of all possible one forms, so these are arbitrary functions. These are like, you can think of them as gradients of like random functions, right? Crazy functions, like highly varying functions. Then, well, we can ask which of them are locally constant when paired against gamma. So now we're asking the local constancy of a differential one form, which is a new concept. Means we need this integration pairing to make sense of it, but it intuitively makes sense. It means like if you vary gamma slightly, so you have a path, and then you like nudge the path ever so slightly, then the integral should be the same. Yeah. And it turns out that's exactly what it's saying. keep the endpoints fixed, vary the path ever so slightly, and then ask for the integral to be constant, locally constant. Now, how do you reason about that? Well, you can use Stokes' theorem directly, right? And to basically characterize these line integrals by the following differential equation.
Yes.
Yeah. So because we have the endpoints fixed,
Right.
we can make a statement that relates the integral along the interior to an evaluation of essentially like the exterior derivative of this one form at the endpoints.
Yes.
And so it just turns into an evaluation of a derivative of the component functions that defined the differential one form. And then there's a relationship between the two because we're asking for local constancy. So that just tells us that we have a system of differential equations. So we can go, we can complete this idea finally by using the fundamental theorem of calculus in this way to relate like this line integral to the evaluation of the antiderivative, right? So the evaluation at the endpoints. And now we're just saying that we arrive at a definition of H1, which is characterized by the gradients being trivially locally constant. So now we just have a direct definition of H1 that falls out of this picture. So what do? We take all the locally constant line integrals and we kill the ones that are trivially locally constant. Right? So we might benefit from pausing for a moment on exactly what's going on here. So we have H0, H1, and we haven't defined anything else. So let's just focus on H0 and H1. H0 is the locally constant functions. So you have a giant space of functions, and then within them you have a differential equation that cuts out the locally constant ones. Right? Now you can map any arbitrary function through the exterior derivative to a one form, and that itself is living inside the space of all one forms, which you can think of as just being spanned by the generating one forms. And it's a huge infinite dimensional space again, because the coefficients here are smooth functions. So, like maybe there are like whatever, 4 generating, if you're in R4, there'll be 4 generating differential forms, dx1, dx2, dx3, dx4, but the coefficients of those 4 forms themselves are functions which themselves are parameters by infinitely many numbers. So if you look at it as like from afar, you're dealing with like this huge thing. But what we're finding is that just by trying to extend the component concept, we get a natural system of differential equations that allows us to cut down to the locally constant differential one forms. And within that locus, right, you have the trivial locally constant ones, which you can pick out just by using the fundamental theorem of calculus. And so we arrive at some meaningful topological information, which is essentially the higher dimensional analog of one-dimensional holes, but in the dual reference frame, which is to say that H1, again, is given by locally constant line integrals modulo the ones that are like trivially vanishing in their variations everywhere. And you do exactly the same thing to get HK again. So you define, you take, instead of line integrals, so that is to say, in this pairing, you're not going to take gamma being a 1 cycle, gamma is going to be a 2 cycle, and a K cycle, and you pair it against a K form. Evaluation is again exactly the same thing. You integrate the K form along the K cycle, and you again ask for local constancy. And the only subtlety is you want to kill those things that are trivially locally constant, like the ones for which
they are themselves D of somebody else.
Exactly. No, that is literally like the ones for which the fact that they're D of something is exactly like equivalent to this characterization by the fundamental theorem of calculus. So now we arrive at HK, which is, without really understanding what a differential form is from any, let's say, algebraic or constructive point of view, we've understood the value of differential forms here from a much deeper point of view, or at least conceptually deeper topological point of view, which is motivated by detecting holes in your space. So you should really think of as the de Rham theory is the correct way to count k-dimensional holes in the dual reference frame. Right? Now we can go on and say that, well, Grassmann's calculus of exterior differential forms is a playground in which you can compute these K holes for any K. I mean, it is itself a number system, with wedge products and addition and multiplication and its own rule system, it's maybe not immediately intuitive, but it's computationally accessible. The rules are very simple, it's very mechanical. And in using the Grassmann calculus, you can actually measure k-dimensional holes in any topological space. Any manifold, we'll see here some ideas that allow you to like cover your manifold by open sets, compute like the totality of like the k-forms that are relevant, patch them together, and then check for local constancy, which just reduces at the end of the day to solving some explicit differential equations that you can derive by hand inductively, using exactly what we just saw. So you want to set the variation to 0, and you want to just kill all of the ones that are coming from like a k-1 form, or the gradient of the k-1 form. So let's just say for now that there is a calculus that allows you to cover any space by open domains, and then you can compute the k groups, the de Rham k groups for the individual pieces and relate them by a kind of gluing procedure. So that means to say that everything just reduces at the end of the day down to open sets in Rn, in which you can compute with explicit coordinates. Right. So, I mean,
that's what a Meyer-Vittori
that's exactly what a Meyer-Vittori sequence is. It's like telling you that there's a lattice in the topology. There's the intersection of U and V as the bottom of the lattice, and there's U, and there's V, and then there's a union of U and V. And the Meyer-Vittori theory just tells you exactly how to relate like HK-1, HK, and HK+1 of all 4 points of this diamond in a precise way. And it really comes down to some intuitive gluing procedure. I mean, say you have a differential one form or a function or whatever defined with one chart, and it's defined on the other chart, and on the overlap they agree, and then you hit them with the exterior derivative of one piece, and then on the other piece, because they agree on the middle, then there's another way to glue the result. And like this is exactly what one does in the Meyer-Vittori theory.
So why is there D star there?
I mean, it's the induced map. So remember, D is going to move you in some way from HK of X to HK+1 of X.
Yes.
But here we have HK-1 of the intersection getting mapped to HK of X.
Oh.
So that's what the star is just distinguishing. It's the mathematicians being careful, because U intersect V sits inside X.
Yes.
So you have to relate classes of differential forms in some subspace to classes of differential forms, maybe with like 0 support outside of that subspace, and that's what D star is taking into account.
Interesting. Okay.
Yeah, so that's why you have 2 D stars here. They basically like, what it's saying is that the cohomology of the intersection is essentially the gluing datum.
Right.
For gluing some differential form in a lower degree to some differential form in a higher degree. And you can think of this as the union, the disjoint union, really. So here we're like, if you have a disjoint union of topological spaces, then it should be intuitively clear that the differential forms are you're just gonna like take differential forms on here and take differential forms on here and consider them independently in a sense. That's just linear combinations.
Yeah.
And the content of the Meyer-Vittori theory is just that you can proceed inductively this way. And you can, in fact, this is how one computes in manifold theory, cohomology. So you can compute the cohomology of the circle this way by covering it by 2 copies of the real line and gluing differential forms in such a way. So let's I guess one way to say what this intersection, the cohomology group of the intersection, which I really love, the word that Bott uses here, is that it provides like the gluing datum for constructing the cohomology in higher degrees, or in other words, to say it like there's some geometric feedback. So whenever the 2 pieces overlap in a cover, then actually every time there's an overlap, that overlap talks to the higher dimensional cycles. Which is, I mean, in some sense, this is like one of the most fundamental computational ideas in topology.
I see.
Like knowing that, understanding that, like whenever you have a cover, that the overlaps are not only talking, they don't only govern information in the degree, they cross degrees. So like every time you just have a distinct open set, it's like no degree-wise information is transferred, but whenever you have an overlap, you find that like now the k-1 forms on the overlap will talk to or see information about the k forms on the individual pieces or the union. So let's skip over the mechanics of exactly how to glue. We can certainly visit that in another day, and let's just look at like some actual examples, like you know, how does one, what do these cohomology groups look like? So for any smoothly contractible manifold, so for example for Rn or Rk, or you know, in any dimension, it turns out that the de Rham cohomology groups are almost all zero, except in degree zero. So that's to say that the only interesting differential k forms that like can be paired against k cycles in any interesting way are in dimension zero.
Yes.
So they're evaluations of functions at points. And that's saying that there's no non-trivial topology in Rn, or equivalently that it's contractible, like that it can be squashed smoothly down to a point. Now, with this specific example under our belt, and we'll see another one very, very soon, we should also point out something very essential about the de Rham theory, which is intuitively clear. We didn't even need to declare it from our presentation as the dual, simplified dual of the homotopy groups. You can see that there's some homotopy invariance of the de Rham theory, and it showed up at every step of the way, right? It showed up when we defined the homotopy groups. It showed up when we dualized. It showed up when we like killed local triviality and so on. Because remember, when you're evaluating the cycle, we were asking for small perturbations, and we're asking for invariance under small perturbations. That's what local constancy means.
Yes.
So how can one understand the homotopy invariance of the de Rham theory without going through that like dual point of view? Well, it turns out that you can stay on the one side of the duality and arrive at it, and it's important to know that. It really just comes from the fundamental theorem of calculus, which, you know, maybe if you know analysis well enough, then this will be clear. You know, it's basically saying that, okay, if you have a path, right, and you try to do a line integral along that path, the fundamental theorem of calculus tells you it doesn't matter how you perturb the path, right? What really mattered at the end of the day was like the topological data of where the path started and ended. As long as you're smoothly moving the path, right, and the one form is well behaved enough, it just cannot detect those homotopy variations. So every line integral on R1, right, is in fact a gradient. So that tells you that the first cohomology group of R1 is zero. Because if every line integral is already a gradient, then they're all trivial. Exactly. Yeah. So now we have homotopy invariance established for the real line, and it in fact works that way in general, like for arbitrary spaces. So you know, like we're just observing here this property in a very like explicit form as coming from the fundamental theorem of calculus. So you don't need to reason about like the homotopy variations of cycles embedded in R1 directly. You can also just know the fundamental theorem of calculus and see the same information. So these two properties, that is to say homotopy and variance, so if you like homotopically deform, remember like the homotopy groups had that property manifestly because every map that we embedded into the space was taken up to homotopy to begin with. So you can tell, all right, you can either deform the map or you can deform the space. It's like you're not doing anything, right? But here you may have to work a little bit harder to see that homotopy invariance. But the fact is that cohomology theories can be in fact defined by these properties. So homotopy invariance is one of the axioms of a cohomology theory. So, you know, in fact, one can go so far as to say, like, differential forms form this perfect model in which we can see all of these properties like on the nose through analytic or calculus constructions. But if one wanted to define an abstract cohomology theory, you could just say, hey, give me a rule that says for any topological space, it gives me a sequence of vector spaces that are related by something like the exterior derivative, right? And have some properties, and those properties are homotopy invariance is one of the fundamental property, and like essential triviality for contractible spaces is another one of those properties. And it turns out that you have a functor that gives you a sequence of vector spaces. So, functor just means like for every manifold, it gives you a sequence of vector spaces, and for every map of manifold, it gives you maps between those vector spaces, and they play well. If it obeys smooth contractibility, so it sends contractible spaces to something that's like one-dimensional in degree 0 and 0 and higher degrees, and also is homotopy invariant, then it is the de Rham functor for smooth manifolds. Like there's one. And it turns out it's just completely determined by these properties, plus Meyer by torus, so plus the gluing, then you have the de Rham functor. And in fact, this is how you can compute the cohomology in general, is just using these three axioms, using local contractibility, using homotopy invariance, and using Meyer by torus. You can compute the cohomology of practically any manifold that you can give a presentation of. So, for example, it's now an exercise for viewers. For the spheres, you basically find, how do they differ from Rn? Essentially, they have the same cohomology in degree 0 as Rn, right, for the n sphere. But in degree n, there's a spike in degree, there's like an amplitude in degree n, which is coming from the cycle of the sphere itself.
Yes.
Right? In the dual point of view, which gives a non-trivial top form.
Yes.
On the sphere, right? That has non-trivial local variations that are still constant. And that's how one can characterize a sphere. So, people will say any topological space that has this property, that's this signature, is basically a cohomological sphere or a homological sphere. Like that, Poincare spheres are examples of spaces that look like this. And, really, really teasing out the consequences for physics here, it's saying that there are some physical constructions that just cannot detect the change in geometry because the cycle theory is the same. Like the cycle content of the space is the same. Another nice example is that the genus G Riemann surface. Now, unlike the homotopy situation where we just have no idea what's going on in sufficiently high degree, although we can see what's going on in certain low degrees, here we can compute precisely what the K groups are. And it turns out that there's exactly one dimension's worth of non-trivial differential forms representing the point class and representing the fundamental class of the whole thing. And then there are 2G circles in degree 1, right? So, and those circles are exactly, you should think of as wrapping the two like symplectic circles around each genus G donut hole, right? Or if you like, they're the two circles in the torus for each genus G handle. And again, the way one computes these results is you take the manifold, you cover it with an atlas of contractible sets.
I see.
And you use contractibility to determine the cohomology on those contractible sets. And then you use the Meyer torus exact sequence along with homotopy invariance to arrive at a complete classification of all possible integrals on the space, right? So it really, really comes down to the existence of cycles at the end of the day, which you can think of as the existence of topological charges. If you want to think of it as a U1 gauge theory, which is completely valid, right? Like, because the differential one forms are just, you can think of them as vector potentials for a U1 gauge theory on space. And really everything we've spoken about here is talking to U1 gauge theory in a highly non-trivial way. So I think we can like, for now, we can probably stop there. I mean, the rest of this is really, I mean, there are a few more key ideas in this introduction which we can go into, which really unpack like two things. So one is the cohomology groups themselves have a duality theory to them, which is called Poincare duality. And that too stems directly from the integral pairing. So it's just another manifestation of the same integration evaluation that we were doing earlier. there's a variation of the de Rham theory called de Rham theory of compact supports. And really, you do exactly what we said, but you replace everywhere there was a function or a locally constant function, you just prescribe that function as compact support. And now you get a different de Rham theory. This is the de Rham theory of compact supports. And it turns out that the de Rham theory of compact supports is dual under Poincare duality to the de Rham theory of non-compact support.
Right, because it's kind of like how you define delta.
Correct, absolutely. It's exactly the same idea. That is correct. That is exactly correct. And you may ask, like, okay, why do you have this issue? And it's just because for the integral to even be defined,
yes,
you need compact support. Otherwise, you know, again, these distinctions vanish if the space is compact.
In the first place, yeah.
Yeah, which we agreed. So that's why maybe we don't need to go into it. But the point is just that the duality does work. The duality between cohomology groups and homology works in arbitrary generality if one takes into account that on the one side you have to take cohomology with compact support, and on the other side you have to take cycles,
yes,
arbitrary cycles. So, and then those are the things that can be paired in sufficient generality. So if you're dealing with an infinite dimensional non-compact space, then maybe you have to worry about this. But let's say, for now, you can look at what the groups for the compact support look like, and it's an amusing sort of like observation that they just look like the same cohomology groups but upside down. So like everything that was in like the lowest degree is now showing up in highest degree, and vice versa, which is part of the duality, in fact. And now, you know, you can study this slightly modified de Rham theory, which is really the same theory. You just restricted the class of functions. You know, instead of taking an arbitrary function, you just narrow down your test probes. And you can check again by hand that all the properties are satisfied. So you've got, you know, your minor bitorus, and one of them fails. And if I recall correctly, it might be like homotopy invariance that fails with the compact. In general. So we can go on a little bit more and talk about the internal structure of differential forms with respect to the Grassmann calculus. So essentially, one of the foundational mechanics of this de Rham theory is that the duality operates via integration paired with the algebraic structure that lives on differential forms. And this is what allows all the calculation, because integrals can be calculated if one is sufficiently deft enough, and the differential forms can be directly manipulated if one is, again, deft enough. And what does it mean to be manipulated? Well, it's just saying that there's an algebra or an arithmetic on differential forms, which is just saying you can take a degree P form, you can take a degree Q form, and you can form a P plus Q form. And it has a graded commutative ring structure. So you can multiply them, and you know, it's commutative up to commuting the signs out. So that's what graded commutative means. It's commutative up to remembering these signs. And I guess this leads to something like quite important, which is that this ring structure, this multiplication, descends to a multiplication on de Rham classes. So remember, like the de Rham groups themselves, how did we define them? We took like basically the kernel of D, mapping from K forms to K plus 1 forms, and we killed the image of D, mapping from K minus forms into K forms, right? So when you restrict to this like construction, you can descend the product, because you could take two forms, you can multiply them, and you can ask, all right, under this equivalence relation we just construct, can you still multiply? And it is true that it becomes literally commutative. So the grading constraint vanishes once you pass to this equivalence class. Now you get an actual ring structure. And not only do you have a ring structure, but again, if you have a form of compact support, say in dimension n minus p, where n is the total dimension and p is like essentially accounting for the upside down nature of the compactly supported theory, we're basically going to like walk down from the top instead of walk up from the bottom, then you can integrate over any cycle sorry, you can integrate over the whole manifold with a new pairing that's different from pairing with the cycle. Okay, it's the same pairing,
Yes.
but we're taking as input not a cycle. So we're not pairing homology and cohomology. We're pairing cohomology and cohomology in different degrees,
Yes.
right? And this is what we said in words earlier. We're seeing it now in formulas that the compactly supported cohomology can be paired with any cohomology class to get a more sophisticated version of Poincare duality. So this is like, in some sense, like the ultimate formulation of Poincare duality in arbitrary generality, which again, you can just throw away the compact supports if the space is actually compact. Now you can see that Poincare duality can be understood either between homology and cohomology or between cohomology and cohomology. So now we arrive at like all the structures of the Durham theory. It's like, you know, it satisfies cutting and gluing, Meyer-Vitorus. It satisfies homotopy invariance, any contractible space. Essentially looks like a point. And why am I blanking? Is this one more property? There are three properties. And so it's smooth contractility, homotopy, invariance. Oh, okay. I said all three of them. Yeah. So and cutting and gluing. So but there's more. It also satisfies Poincare duality. So you have a perfect pairing on cohomology. Let's assume it's compact. So you just have a perfect pairing. You can, you know, most of the time it's 0 if the complementary degrees don't add up to the dimension of the manifold. But you can think of it as just coming from, you take a degree P plus P1 form and a degree P2 form. And if P1 plus P2 adds up to the dimension, then you can integrate the result over the whole thing. And then you get a number, and this pairing is perfect, which tells you that the spaces are dual. It tells you that there's a palindromic structure to the Euler signature, if you want, which is the dimensions of the cohomology groups.
Right.
And there's a ring structure. There's a commutative ring structure on cohomology, which descends from the ring structure on differential forms. So this is a heck of a lot of structure, right? Like, you know, maybe in the homotopy theory, we had some groups, and those groups detected the signature of the manifold. But now we're saying in the cohomology theory, even though we've simplified things greatly, there's still this wealth of structure that shows up under these equivalence classes of integrals that you can perform on the space, essentially. And this manifests in like this palindromic structure that comes from the perfect pairing, and manifests in the ring structure. It manifests in like the fact that these numbers have topological significance, telling you like they're essentially an approximation, if you want, to the number of n-dimensional holes in the space, and so on, and so on. We can either choose to, maybe we should actually, I'm not going to go too much more into Poincare duality, quite simply because if we really want to do Poincare duality, we should do that as its own thing, because we should treat Poincare's lemma, which is, you know, there's one question that's unanswered here, which is that, okay, it's all fine and well to say that like cohomology is dual to homology, at least, or dual to homotopy after simplification. But give me a differential form. How do I cook up a dual cycle?
Right.
Yeah. Like that's like saying somehow like I have a distribution, but I want to know like the support of this distribution, right? So there's a way to like really do that in a precise way, and we can like really construct the Poincare dual cycle to any cohomology class, which is it's actually really important if you want to do any calculations. But that goes through something called Poincare's lemma, and we should
where over this D.
Yeah, no, precisely, and it again comes down to like really understanding the differential equations that are involved.
No, that does sound good. It would be interesting also to take the sort of complementary physics perspective involving supersymmetric quantum mechanics.
I agree. Maybe that's what we should do next.
Yeah. Definitely.
So I do want to say one thing, which is that your point earlier, Basu, can be most naturally about delta functions and currents can most naturally be understood through Poincare's lemma, which is to say, okay, a delta function, you can think of it, if you enlarge your class of functions big enough, then well, a delta function is going to show up in your cohomology theory, right?
Yes, yes.
It might represent some cohomology class. So what's the dual cycle? Well, it should be a point.
Yes, yes.
Yeah, and that's the end result, is that really understanding that is what is used to be called Durand's theory of currents.
Right, right.
Yeah. Which speaks to the physical notion of a current.
Exactly, yeah.
Precisely. Like it is the physical notion of a current.
No, for sure, for sure. That is
and more generally, you can replace the points by submanifolds, and there's a way of doing that. And again, that's Poincaré's lemma. So maybe the very last thing, okay, there's something very deep here involving fiber bundle theory, like classifying vector bundles and principal bundles, and actually Durand theory was in a sense motivated because every fiber bundle has a cohomological signature, which is it's a series of cohomology classes which you can think of as the amplitude of the bundle, and you can classify all possible bundles by knowing all possible signatures of bundles. But let's not talk about that. It's a much harder. It's a little few episodes away, but what we can do is very briefly look at the fact is that the Durand theory came from the theory of currents. That is fundamentally, we presented it in its now complete form.
Yes.
In terms of n-dimensional holes, right? But the intuition came from electromagnetism, which is where we started. So I think we should end there.
Sure.
Right? So first of all, it shouldn't be surprising that the equations of mathematical physics would interact so deeply with topology, because as you pointed out, with Gauss's law, it's been present from the beginning.
Right.
So, we can be super precise about what you said earlier, Vasu. So in a vacuum, right? No charge no extra charge content.
Yes.
So that means to say that all charges possible are only going to be topological, and they're going to come from the manifest structure of space-time with no extra things floating around. Then the magnetic field can be represented by a two-form in R4, which now we're not talking about the vector potential here, right? We're essentially talking about its curvature.
Yeah.
And here's an explicit form of it, just literally written in coordinates, right? Which, I mean, any self-respecting student of electromagnetism has hopefully seen before. Speaking out the electric and magnetic components of this curvature two form. And it's important that the form omega is locally constant in our sense, right? And that's inherent to Maxwell's equations, essentially, right?
It is part of it.
Yeah. So you can, using the Lorentz metric in R4, we can find what is sometimes in mathematics called the Hodge star of a two form, which in R4 maps you to another two form. So the Hodge star is a symmetry on the space of forms which uses the metric in a contraction sense, and it usually maps a k form to an n minus k form. But because we're in dimension 4, and this is very special in dimension 4, that the Hodge star is an involution on two forms, and so it will map a curvature to another curvature.
Correct.
Which again can be described in some very explicit form, and fundamentally comes down to electromagnetic duality.
Yeah.
Right? So Maxwell's equations in totality are literally in the vacua are that the exterior derivative of the curvature two form and its Hodge star are zero. That is the most succinct way of the in vacua Maxwell's equations. And then in particular, it says that we have a cohomology. Remember, you can only talk about a cohomology class if it's annihilated by D, right? We defined the H2 to be the space of solutions to D modulo the ones that come from a lower degree form. So that's telling you that fundamentally Maxwell's equations just restricts to those two forms that are cohomological, that have cohomological significance. And so the domain of electromagnetism is entirely within the language that we have constructed. So you might have worried in the beginning, are we being overly prescriptive or something? And the answer is no. In fact, Durand's theory is cooked up so that everything physically relevant is captured by the Durand theory. And now we can look at some extremely simple concrete example. Like let's be super concrete. So we'll consider the Coulomb potential of a point charge at rest, say at the origin. So in R4, so it's 0, 0, 0, 0, right? Will generate an electromagnetic field, omega, which again, we're going to represent as a 2 form, right? And we can represent it very simply in coordinates, right? As like scaled by the charge, which we think is quantized at some particular value, the exterior derivative of a radial field. Yeah. So this is the potential, right?
Yes.
This is literally like the you can think of it as one way of representing the potential. It's not literally what is called the U1 vector potential, because for that we're going to take a curvature. I mean, in this case, it might literally even coincide.
No,
it literally coincides, yeah. And here we just take R to be like radial. Yeah. So we're just dealing in the radial coordinate frame. So this tells us that if we throw away the time axis, then this 2 form will be everywhere defined. Yeah. And you can just ask, what is the Durham cohomology of this set? Like, okay, just like elide, like cut out the time axis where this thing is not defined. And what is the cohomology? Again, that's going to reduce to like, what is all possible, like curvatures, and what is all possible magnetic fields that this space-time supports? Exactly. And it turns out that there's a very nice answer. This thing is basically a sphere.
Yes.
It's a 2-sphere.
Right.
Cohomologically. That is to say, physically, space-time is no different from a 2-sphere.
Yes.
At least in terms of the E and M content. And this tells us that, well, just the explicit expression of omega tells us that nothing is going on as a 2 form. Why? Because d squared is 0.
Yes.
Right? So this is locally, this is not just locally trivial under variations, it's like trivially trivial, right? It's like already 0 because d of it is 0. And the reason is because it's already the image of something, and that thing is already locally constant. Not just like under variations. It is on the nose locally constant. But on the other hand, the star, so the electromagnetic dual field, is given in explicit coordinates by something that may be familiar. And this is a generator of H2, which we saw earlier, right? It is one-dimensional. And so there is, like, omega might have been 0, but its dual field in Maxwell's theory is non-zero. And in fact, it's non-zero, it generates all possible integrals in the appropriate dimension. And so we can just even physically define the class of star of omega as the charge.
Yes.
Right?
Correct.
So the source was like the point at the origin, and now we play this game and we've translated, and now we have a definition of the charge. So, what this is saying is that, electromagnetism is no different fundamentally from the foundational equations of topology, right? And these are one and the same. There's no distinction. And, whether or not one accesses the information from the electromagnetic point of view or the topological point of view has different ramifications conceptually. Like, it suggests very different ideas, but the information is the same.
Correct. Oh, the electromagnetic story goes through the construction of a U1 bundle if you start from the very beginning.
Right.
But what we'll see maybe next time is the story with Britain came up with, where you can directly just get to the graphing wall. Right.
And you don't, so Witten's genius, you could say, is that, we have a U1 gauge theory. It's a very complicated construction. I mean, it involves like many things that we, if you really want to write down U1 gauge theory, we have to talk about fiber bundles. We have to talk about principal bundles for circles. We have to talk about the Lie algebra bundles. We have to introduce all this pretty sophisticated machinery to even talk about a gauge field, even though we literally did that here almost in coordinates directly. However, there is a much simpler physical construction, which is a supersymmetric quantum mechanics propagating in the manifold you started with, that relies on everything we saw here today. So we saw the the cohomology groups HK, and then when we put them all together, we took the direct sum of HK, we found there's a ring structure. You can multiply two cohomology classes. We found there's a pairing, which means you can like you can pair and integrate to evaluate. So there's a duality or a palindromic duality structure. All of those things have physical significance when interpreted as a supersymmetric quantum mechanics of a supersymmetric particle propagating in the manifold. And it's actually not incredibly clear to me the relationship between the U1 gauge theory point of view and the topological mechanics point of view.
It isn't.
It's certainly not clear to me, although we can investigate both of these.
Yeah, there is a possible point of contact, but we'll get to that later. Involving the Whirling formalism for spinning fields.
Yeah, that would be extremely interesting. Yeah,
it has
that would be extremely interesting to see. I mean, I think for material wise, we should probably stop there. That's
yes. So